Hello everyone. So we'll be continuing on, and this is the last topic on transverse vibration. So it's very important for us to understand what is critical or whirling speed of a shaft, Um and we'll learn how to calculate the speed of the critical speed of a shaft. Okay. So before we go ahead and I explain the concept behind it, we need to understand that in actual practice a rotating shaft carries different mountings and accessories on it. So if you see this particular diagram, this will be a schematic diagram of a shaft axis. Okay, on this axis we'll have different mountings and accessories on it, like bearings or pulleys or gears. So what happens here is, when the gears and pulleys are put on the shaft, the center of gravity of the pulley may not coincide with, or basically does not coincide with, the axis of the shaft. Okay, and that is so we need to understand that the center of gravity G of the pulley will not coincide with the axis of the shaft. So what happens here is, the distance between the center of gravity of the pulley and the gears or the mountings and the axis, there is a distance between both the points. Okay, so because of this, there's a certain distance between the axis. This creates a centrifugal force on the axis. Alright, so this force, centrifugal force, when the shaft is stationary, it tends to bend the shaft. Okay, and because it bends the shaft, furthermore the distance increases between the center of gravity of the mountings and the axis. And when the shaft is rotating, this distance even more increases. So if you notice here, there's E plus Y. The distance between the center of gravity of the mountings and the axis of the shaft, that is the center of gravity of the shaft, the distance increases even more. So this all can also lead, if it increases much more, this also can lead to bending of the shaft, as well as it can also lead to the shaft the shaft can also break. Okay, so bending of the shaft not only depends on the value of eccentricity. Okay, it also depends on the speed with which it rotates. So it's really important for us to understand that the effect of the centrifugal force, it increases, and finally the shaft can break. So there is a point at which the speed at which the shaft runs, so that additional deflection takes place, okay, from the axis of rotation. When it is at infinite, when that point is infinite, that is known as the critical or the whirling speed. So it's not just the eccentricity but also the speed of the shaft which increases the distance between the center of gravity and the axis of the shaft. So I hope you're able to understand that what exactly is critical speed. So by definition, I just want to define and read out the definition here. The speed at which the shaft runs, so that additional deflection of the shaft from the axis of the rotation becomes infinite. That speed is known as critical or whirling speed. So the critical or whirling speed will be given in terms of revolution per second. And the formula is 1 by 2 pi root of g by deflection. And if you write the value of g, you will get 0.4985, and simplify it further, you'll get 0.4985 by root deflection. And if you notice, this formula is exactly same as the formula for natural frequency of transverse vibration, but the unit is revolutions per second. So let me explain it once again. You need to understand that if you have a shaft, on the shaft axis there are different mountings which are attached. Because of those mountings, there's a centrifugal force acting on the shaft which tends the shaft to bend. That is when the shaft is stationary. But when it starts rotating, because of the speed of the rotation, Furthermore, the center of gravity shifts downwards, and this creates even increases the centrifugal force, and it can also lead to the rupture or breaking of the shaft. So it's very important for us to understand and calculate the critical or whirling speed of the shaft, so that we can maintain the additional deflection, and we can design the shaft and the mountings in such a manner that it does not exceed the critical speed, and we can also avoid the breaking of the shaft. So that design is very important. So for every problem, when we calculate the natural frequency, we should also calculate the critical speed. So if we calculate the natural frequency, we can automatically know what should be the critical speed of the shaft. So keeping this in mind, let's do one problem for today, only one problem. So we will take the example number 23.6. Okay, I'll read out the problem for you. A shaft 1.5 meter long, supported in flexible bearings at the ends, carries two wheels, each of 50 kg mass.